Let's do number 9. We have an RC circuit, and we have that the capacitor is going to charge. So it's connected to voltage, so we know that we have the voltage source, we have the capacitor, we have the resistor, and the switch is going to be closed so that the capacitor can start to charge. So how long does it take for it to reach 95% of its maximum charge? So we know that when you're charging the capacitor, that initially you're not going to have any charge on it, and then it's going to charge up to the maximum charge. The graph looks like this, the charge per time. So to get to almost its maximum charge, right here, that's 95% of the maximum charge, then we're looking for this time. So we have to find the equation that tells us how charge varies with time for a charging capacitor. And it's this one, where Q0 stands for maximum charge. And we're looking for we're looking for time, but we're not told exactly how much charge we're going to have, but we know that we're going to have 95% of the maximum charge. So what that means is that the Q that we're looking for is 95% of the maximum charge. So by the problem being worded this way, it actually makes the problem easier, because if Q is 0.95 of the maximum, then we don't even need to know what that maximum charge is. We don't even have to calculate this, because it's going to cancel out in the equation, this Q0 and this Q0. So this actually makes the problem easier. We have to solve for time here, so instead of plugging in a time and solving for charge, we're plugging in some charge and solving for time. So you have to be able to do some algebra to get the time by itself. So we have 1 minus the exponent equals 0.95. So if we rearrange this, we're going to get e minus t over tau equals 0.05. I subtracted 0.95, I added the exponent to the other side. To get rid of this exponent, we have to take the natural log. The natural log of this whole thing, if we take the natural log of both sides, then in this case, the natural log of this gets rid of the exponent, and you're left with negative t over tau is equal to log of 0.05. And then we have to solve for time. So just get time by itself, multiply by tau, multiply by negative tau, and time will equal negative log of 0.05 multiplied by tau. And tau is equal to RC. So you need to find tau on the side. Tau is RC. R has 2 times 10 to the 6. C has 3 times 10 to the negative 6. So the 6 and the negative 6 cancel out. So it's just 2 times 3. So it's 6 seconds. So plug in your calculator negative log of 0.05 times 6. And we should get 18 seconds. Let's do number 10. In this circuit segment, what's the potential difference VA minus VB? And it shows us that the current is going to the left. So VA minus VB. So that means that we can think of this as potential difference being final minus initial. This is the final potential, V final, and this is V initial. So that means that we're going from B to A. So imagine that we're going this way. What's the potential difference from B to A? That's what VA minus VB is. So this is really using the loop rule from Kirchhoff's rules, that we're going this way to the left and we're going in the same direction as the current. So when you go in the same direction as the current, for a resistor, you get negative IR for the potential drop here. And then here we're going across a capacitor. So you know that there's a potential difference across your capacitor plates. And to find the potential difference, use the definition of capacitance. C is Q over V, so V is Q over C. But is that a gain or drop? Well, you're going from the negative to the positive. So just like a battery, if you're going from negative to positive, and that's what we did in chapter 18, you know that the potential difference is positive, so it's plus Q over C. And then we're going from the positive terminal to the negative terminal of the battery. So that's a negative 15 volts. So this is the potential difference from B to A. This is what the question's asking for. So we just have to plug in the numbers. 0.007 is the current. The resistance is 15,000. The charge is 50 micro times 10 to negative 6. The capacitance is 0.5 times 10 to negative 6, so those cancel out. And then minus 15. If you plug all that in a calculator, we should get negative 20 volts.